that was the result. It was color coded. When we click in here, we see the left square has gigapascal stress. We haven't looked here at the strain, but that is because there obviously is a lot of strain. Then we get 10 to the 9 Pascal, gigapascal, and the left one it's 10 to the minus 5, so there is a little bit, but it's just numerical precision. And that resulted from a setup. Maybe first of all, in study, that's where you control the solution. Stationary. Here is the mark. If you enable this, then the geometric nonlinearity is included. So that's where you have to know where you have to do something. Basically, that's it. The other thing I did here was just for illustration. If you think the displacement is so large that you should use the exact definition of strain, you just make the mark. Make sure that there is a mark. If you're not sure, you may do two simulations, one with the mark and one without, and then you decide what is the difference and also see how much time you save. Sometimes maybe with a small model then it doesn't matter. But if it's a long, lengthy simulation, what do you think? Should we open again or feel good? Cozy? For me it's a bit dark. If nobody worries, I will open. Climate change protection. Maybe at least like this, to rise up. So this is the main point, talked a lot about the background, but practically you have to be aware of that mark, that you can enable the exact definition of strain. But you learn something, at least that's my idea, if we set up such models. So let's have a look what we did here. The first thing was that we actually used another linear elastic material node. The reason for that is, here in that default mode, usually don't do anything on that, it is defined the geometric nonlinearity. And here I switched from, it's called total Lagrangian. They skipped just the green. Oh, they skipped the green. Interesting. Anyway, I switched here to geometric linear. For the left square, that's why we saw the strain there, because we used linear formulation. You could even see it if you go to equation. I'm not sure if you recognize this, but this is the definition I showed you before. How come? So write it down. So the linear version of strain is used. And the second material I just introduced, usually you don't need this, but sometimes can be useful. So I doubled the default node, and that was set up in a way to have the geometric nonlinearity from study step. I could have explicitly told the program use the Lagrangian formulation. What means from study step? From study step means the program checks what is defined here. If the mark is set, then it uses geometric nonlinearity. Let's go back to this and finally check for the equations. And you see it already checked what is in the study step, and there is a more lengthier expression. I mean, even here you see the transformed version and the not transformed. This is what we discussed, cancels out the parts which make a problem. And how to come from here to the engineering. This is a squared even if it's transferred times not transferred, is a squared version, so you neglect this, and with this you are only linear, which causes the problem in case. Yeah. I hope it was worth to open up the model again, to boil it down for what is important for practical use of COMSOL for solid state simulation. So some things probably you know already. The stress calculated in case with the correct strain definition provides you in 3 dimension this 3 times 3 stress matrix that can be diagonalized, and then from that 3 components you can do the following. If the material you try to model is something like ceramic, then you can use this components, the first principal stress and the third principal stress, to check for maximum positive and negative stress. One is pressure, the other one is, I don't know how it's called, if you pull on it, plus and minus, the 2 directions. For ceramic, obviously, it's more dangerous if you pull on it, then you can burst the whole thing. The ceramics is capable to withstand if you apply pressure. What is the name if you pull on it? Is there a pull? Obviously, pull is okay, but is there a more specialized expression? So, tension. If you apply tension. So, tension and pressure. So, tension is the other sign. Thank you. So probably this is the more important thing. So if you look for that third component, the point is just a practical thing. I mean, COMSOL can calculate this thing, but somehow you have to display what you do with the 3 times 3 matrix, how to make use of this. And for that reason, it's very good if you have just simple parameters like that third principal stress, which you can plot, and then you can find out where you have the maximum strain. No, not strain, tension, maximum tension. And then, of course, you are interested in to avoid bursting the material. The other thing for durable materials like metals, the Van Mises stress, which is actually also calculated from the things you get from diagonalizing the stress. And you see these 3 components are combined in a certain way. Some smart people found out, maybe you know better than me, why it's a good idea to combine it that way. But anyway, with this you again can calculate a number which you can somehow display and make use of. And this yield value tells you if you are safe, if you operate it in that way or not. Just to add up a little bit. Now, there are more simulation or study cases. We so far discussed only static, stationary simulations. Next thing I like to discuss with you is time dependent, but I think I will not do it today, at least not finish, maybe even not really start, just some motivation at the beginning. Here we have time dependent things. If time dependent things try to be calculated, they need to be time derivatives, otherwise not possible. You remember the things we discussed first. So time derivatives for what quantity? For the displacement. Here we discussed why the displacement comes in here is a bit complicated with the Hooke's law and the strain definition, but here is explicitly. So we have a first derivative of the displacement and second derivative, and we have various coefficients in front. That may remind you to what you know from oscillators, spring mass oscillator. This is something which looks a little bit like velocity, doesn't it? U derived regarding time, and this is like acceleration. So this is like acceleration, and what could this be if this is acceleration? Spring mass, there would be a mass. Here is the mass density. That is typical for a type of formulation that you have density quantities. Here we don't have force, but we have a force density, force per square meter. And this parameter is some damping mechanism. Time transit simulation would mean we don't put a static force and then wonder what is the stress and strain in here, but make some time changing things. For example, by having time variant force, outside force or volume forces. And if you would do this, then you accelerate all the elements in here, so just Newton's law. It's still a balanced equation of forces, and that thing here is a friction force. If the elements have a certain velocity, or at least that is the way it's modeled, that means there are friction forces proportional somehow to something like a velocity. From macroscopic physics, for example, driving a car, there are sometimes also friction forces not linear with the velocity. In case of car, is quadratic with velocity. That's why the fuel consumption rises up if you drive fast. You could also do this, but what would it mean? Then you would have here a square of that term. Good to do, but what would be the impact if you square this? You make this a nonlinear equation with a lot of trouble, which may arise. So that's why usually things are modeled that way. The details of this we discuss next time. Here is just the equation and the labeling of the constants. And next time, tomorrow, I will do some practical thing again. We would continue with our demo flat bar or demo. You see, I just did in the morning. That's also the reason why the slides are not updated. I will provide them afterwards. And tomorrow, if we meet again, we would continue on the static model and make a time simulation. So we let the thing oscillate. And just to give you also some idea, what we also do is frequency investigations, eigenfrequency we probably don't do, but I definitely want to show you. No, eigenfrequency we definitely do, in which most things oscillate, but we will not, maybe I think not, do frequency analysis. So, was quite a demanding lecture, at least I had the feeling, also for me, probably also for you, maybe, I don't know. Anyway, that's for today. Thank you for your attention. Have a nice Wednesday. Thank you. And tomorrow, that's also the message, we do again more practical.